So again, as always, very good to be back with you. And I want to talk today about how to figure out the mass moment of inertia of a tire. Okay? Well, if mass moment of inertia is the resistance to rotational acceleration, well, the mass moment of inertia of tires should matter when you're trying to figure out what the performance of a car ought to be, right? Makes sense. The harder it is to spin your tires up, the harder it's going to be to accelerate your car. Now, cars weigh a lot more than just the tires, so it's not necessarily a huge contribution, but it's not zero either. So what I got a little tire. All right, this is a tire off a racing go-kart, and it is a Bridgestone. I'm not sure what this is, 4.5-10.5. So this is just a little baby racing tire. And you can kind of see here, it's got a rim in it, okay? And it doesn't weigh very much. It's a few kilograms here. But at the university where I'm at, Purdue, we have an annual go-kart race up on a track we have, and this is one of the racing tires off one of those go-karts. So we're going to work with this, okay? So what we're going to do this is in two steps. First, I'm going to show you how to figure out the mass moment of inertia from a measurement, and then we're going to make that measurement. Okay, sounds good. So here's how this works. Let's say I've got a tire rolling down a ramp, which is what I'm going to do here in a second. Okay, there's a tire. That's not the roundest. It's not the roundest tire in the world, but okay. Okay, and it's rolling down a ramp with an angle theta. Okay, so let's look at what forces are acting on this tire, forces and moments both. Okay, so there's what it looks like. Let's go over here, I guess. That's slightly less terrible. Okay, so there's the friction force. Okay, friction force goes that way. Weight goes this way. That's mg. And then I'm going to do this. I'm going to have a coordinate system, x and y here. And then there's the moment that goes with it. Those are the positive directions. Now the reason I'm making this parallel to the ramp is it makes the bookkeeping a little easier. You don't have to put it that way if you don't want to. If you'd rather have the, looks like an L, if you were going to have the coordinate system horizontal and vertical, you can do that. That's okay. There's nothing mathematically wrong with this. Rule number one of physics is that the physics doesn't care what coordinate system you use. Well, I'm going to use this one just because it makes things a little less difficult to work with. Okay, so there's mg, and that's going to be sine theta, and that's mg cosine theta. Okay, and I think I've mentioned that before in some of the other videos about how to find those, but I guess just for completeness here, if that's mg, okay, that's the component of mg in the y direction, and that's the component of mg in the x direction. Well, so all you really need to know now is, this is about 40 or a 90 degree angle. Is that theta or is that theta? Well, if this gets small, this is theta here, okay? All right, if this angle got lower and lower and lower, that's the angle that would get closer and closer to zero. So if this is the hypotenuse, okay, I'm running out of space here. Okay, that divided by that is cosine, and that divided by that is sine. So that's going to be mg cosine theta, and that's mg sine theta. So that's where that comes from, okay? So let's see, I've got that and I've got that. Now, I'm going to, if you don't mind, since we've already got this, I'm going to erase this right now. You can take a screenshot or whatever if you need to. And I'm going to erase this because I need that. Okay, now the way we teach, I'm in engineering technology is my department, and so we teach students using what we call inertial force or inertial moments. If you say F equals ma, those are the inertial force or the external forces. Get my head out of your way here in a second. There we go. Right there, ma has the units of force. Now, is it a force? No, not in the strictest sense. It's not. But if I treat it like a force and push it around like a force and draw it on my free body diagrams like a force, I always get the right answer. So we teach our students to draw that inertial force on the free body diagram as if it was an external force. And guess what? You always get the right answer. Now, before the Grinter report, before engineering went to engineering science and split off from engineering technology, everybody learned it this way. My dad, when he went to college in the mid-50s, I think, did it this way. Okay, so we didn't invent this. So we need to know where the accelerations go. The acceleration goes there and there. Okay, those are the accelerations, right? And the inertial forces and the inertial moment act in the opposite direction of the acceleration. So that's the inertial force, and that's ma in the x direction, and this is the inertial acceleration, m inertial, and that's I alpha. Okay, and that's just a way of putting the right-hand side of Newton's laws onto the diagram. If you prefer to just sum the forces and set them equal to ma, absolutely fine. It's mathematically equivalent, doesn't matter which one you do. All right, and I certainly understand if you would prefer to do it that way. This is no longer in fashion. It used to be the standard way of teaching this kind of problem. So here we go. We've got all the forces on here. Friction force, all these, the weight and all this kind of thing. By the way, that component right there is what makes the tire roll down a ramp. Okay, without that it wouldn't roll. So we've got everything here. Now the only thing I really care about is the acceleration. Okay, what I'm trying to do here is step one. I should have written this down. Find ax or alpha. Either I can live with either one. I probably want ax. Okay, well, if that's all I want to do, I don't have to sum the forces and the moments. I can just sum the moments if I'm clever about how to do it. With this diagram, you can do two things. You can sum the forces and you can sum the moments. Well, there's a lot of stuff I don't care about. You know, I don't really care about what that is, and I really don't care what that is. I'm going to assume that the tire does not slide going down the ramp. But as long as it doesn't slide, I don't care what that force is. So if I'm not going to care about a bunch of these forces, let's see that point right there. Okay, I'm going to sum the moments about that point. And the reason I'm going to sum the moments about that point is I've done this a few times before, a few thousand times before probably. And if I sum the moments about that point, I only get the stuff I care about. All right. Okay, if you happen to do it the other way and sum the forces and the moments, that's absolutely fine. You're not doing a thing wrong. Okay. So I need to call this something. I guess I'll call it, I don't know, shall I call it P for point? Class the other day we called it Dave, and that worked out okay too. So I'll sum the moments around the point P, and I'm going to set them equal to 0. The reason I set them equal to 0 and not I alpha is I alpha already lives in there. Okay, I've already taken that into account, so I get to do that. And the reason we do this for our students in engineering technology is by doing things this way, this problem starts to look an awful lot like a statics problem. Instead of being static equilibrium, now it's a dynamic equilibrium. So it's a very consistent way to build on knowledge we already have. So let's just do this. Well, okay, there's going to be the radius, by the way, is r. Okay, take that force times that radius. Okay, and that's going to equal a moment. Well, that force going that direction is going to give me a counterclockwise moment, so that's positive. All right, so I go R, M, A, X. There we go. There's that one taken care of, so let's check that one off. This one, okay, that is I alpha, also in the positive, assumed positive direction. All right, so I can check that one off. And that one is going to be minus, whoops, R, M, G, sine theta, and that all equals 0. Again, it equals 0 because I alpha already lives in there. Okay, so there's the only three things I care about. I don't care what that is because it goes right through the point I'm summing about, and I don't care what that one is for the same reason. This one I don't care about because I've already broken it into its two components. I've already taken that into account. Okay, the components of this are already there, and they're already included them in my equation. So I'm going to let me check real quick and make sure I haven't had a stupid attack. Yep, that looks good. So I've taken those three into account. That's good. So what am I going to solve for? Well, I want AX. I want that. But I got that in there. What am I going to do? Well, if no slipping, if there's no slipping, then, and I'll get my head out of your way so don't freak out here, alpha, I'm sorry, okay, A sub x equals R alpha, if you're not slipping. And the reason I know that is, let's see, S equals R theta. And you might have learned that in junior high school or something. That's the distance traveled as a arc length traveled as a circle rotates. Well, take the derivatives of that. Well, that's a distance. What's that? A velocity equals R omega. And we can, it only has one term because R is just a constant and derivative of R is 0. And so the last thing, we get A equals R alpha. That's this. Okay, so that's where that comes from. Derivative, derivative. So if you if you're on an exam and you're freaking out, you know what, you can't remember this, this is how to derive it. It's very, very simple. You could write this down on the side of your paper if you need to. So if you do all that, do a little bit of algebra here, and we're trying to find the mass moment of inertia. That's the big goal here. Well, if we solve for alpha, or for I, now can you guys see that okay? Oh yeah, we got plenty of room here. Okay, I'm going to just write this down rather than rederive it for you. You can work this out as well as I can. Give me a second here. Okay, so there you go. There's the expression for I. That's the goal. Okay, we're trying to find this. So that I've got it on the left-hand side. That's great. All I got to do is know all this stuff on the right-hand side. Well, how am I going to do that? Well, let's see. R. Easy. I can measure. I can just get a tape measure and measure that. Mass, I've got a scale down here, so I'll measure that in a second. A. How am I going to do that? Well, what I'm going to do is I'm going to take that little tire here and I'm going to roll it down a ramp in the hallway, and you'll see it here in a second. Sine theta. Well, as long as I know what theta is, that's easy. And mass. Okay, I had that up before. Geez, 9.81. I'm good. All I have to do is figure out how long it takes my tire to go a certain distance and back out acceleration from that, and I'll be able to calculate I. So, got the math worked out. Let me get this out. Let me get out of your way again. Okay, we've got the math worked out right here. Let's go do an experiment, okay? Okay, we need to know how much the tire weighs. So there it is, sitting on a scale on my desk here. Okay, there's the tire. And just to make sure you guys can see that, there you go. Okay, all right, so if I can get down here. There we go. There's the ramp all set up. Tires on the ramp. Got some books holding the ramp up. It's around 6 degrees. I'll show you how to figure that out here in a second. That's Davin. He's going to sit here and watch the test with us. Okay, so I'm going to let this go. I'm going to have to give this a little bit of a push to keep it on the ramp, but we'll take that into account. So ready? Go. And there you go. Okay, that's all the data we needed. The marks on the ramp are 10 centimeters apart. So let's take this data and do something with it. Okay, we're back now. We've got all our data. And let's go through some of the stuff we've already seen and some of the stuff we had to infer from the test, okay? So mass, okay, 1.63 kilograms. We already knew what that was. I showed you that. Radius, well, that was really hard. I took a ruler and figured out what the radius was. I need to know what the angle is, the angle of the ramp. Well, I measured up the ramp. It was 1.65 meters between the 2 points I used. And the change in height between those 2 points was 0.155 meters. I actually did this in millimeters, but there it is in meters. And that works out to 5.39 degrees. Although it turns out what we need in our calculation is actually the sine of theta. So you don't even really need to know theta as long as you know those two numbers. Now, the one that's a little less obvious is how do you get acceleration from the data we measured? Well, that board has marks every 10 centimeters, right? We saw that here. In fact, here you go. Here, pull this thing out. There it is again. Maybe you can see this. I've got these marks on here. Those are 10 centimeters apart. You can see that if you scroll back in the video, you can see that. So what I was able to do was go through the video I shot, we just saw of the tire rolling down the ramp, and look at the times it took to reach those different points. Well, when I did, I plotted those points. I put time there and position there, and what I got was a parabola, very close to a parabola, and it should be a parabola. Constant acceleration gives you a parabola, so I did this in Excel. Okay, if you want, I'll hold the paper up to the screen. And this is what it gave me when I hit the Add Trend Line button. So this is a parabolic fit to my data. A parabolic fit means a second order polynomial. Okay, and I just did that using the Add Trend Line button. And there's what it gave me. Okay, well, how do I get acceleration out of that? Well, we already know an expression for constant acceleration, for displacement because of constant acceleration. It's 1/2 at squared plus v0t plus x0. All right. Well, there's x0. It's a long board. It's about 2 meters, so there it is. There was the initial velocity in, let's see, what's that going to be? This is going to be in centimeters right now. So centimeters per second. That right there is 1/2 a. We'll take that, double it, and turn it into meters per second, and you get 0.575 meters per second. So we've got all the data we needed for that expression. Mass, radius, sine theta, and acceleration. We're in business. All we've got to do now is take all those numbers and plug them back into the equation that we derived at the beginning of this video. So I'm going to do that real quick. Give me just a second to erase this. And when I do, all right, so just give me a second. I'll write this back up here. I equals r squared, okay, mg over a sine theta minus m. Okay, now the units for mass moment of inertia are going to be kilogram meter squared, so this is going to be in kilograms meter squared. Okay, kilograms, then acceleration of acceleration cancels out. That's unitless. That's kilograms. We're in business. So if I work all that out, I'm going to get, let's see, my mass was here. There you go. My radius, I should say. If I do that, I get 0.126 meters squared times 1.630 kilograms times 9.81 meters per second squared over. Now here's where I get to put that acceleration in that I got from the curve fit, and that was 0.575 meters per second squared. Okay, sine theta, that was 0.155 over 1.65. Turns out to be just a tick less than 6 degrees. It was 5.39 degrees, but it turns out it doesn't really matter. Okay, that is sine theta. Last thing I need to know is 1.630 kilogram. There's the expression. Work this out, and what you finally get is 0.016 kilogram meters squared. Okay, a lot of work to do it the first time, but once you've done it once, it's really easy to do it again, and you can write this all up in maybe an Excel spreadsheet or something like that. So this little wheel, tire, has a mass of 1.63 kilograms and a mass moment of inertia of 0.16 kilogram meter per second squared, and we verified that experimentally. So I hope this helps, and I'll talk to you next time.